The chief guest or chief speaker of this technical session is Dr. Shyamkant W. Anwane sir, who is Associate Professor and Head of the Department of Physics at Sri Shivaji Science College, Nagpur. He did Masters in Physics in 1992 and was conferred with Doctorate in Physics by the Nagpur University in the year 2000. During his full-time PhD program, he bagged prestigious Senior Research Fellowship twice by Council of Scientific and Industrial Research, New Delhi. He has visited many international universities so far. To reach students at large, he wrote 4 books, 2 of which are recommended by Amravati University in the curriculum of the first year and second year BE program. He is nominated on the Board of Studies of Physics at Bajaj College of Science, Varda. He has contributed a chapter entitled Solid Electrolytes, Principles and Applications for a research book titled Advanced Energy Materials, published by Scrivener Publishing House. He has completed 1 minor research project entitled Interactive Physics by Simulations Using Maple. He is a recognized supervisor of Nagpur University for PhD program. His research interests include solid state ionics, solid state electrochemical, SO2 gas sensors, special relativity and general relativity. So this is all about Dr. Shyamkant Anwane sir. I welcome Dr. Anwane sir and once again Dr. Avtar sir in this technical session. Thank you very much.
Thank you, Professor. Now with great pleasure. Thank you, Kharshe sir. Am I audible? Thank you. Once again, thank you, Kharshe sir. Now, with great pleasure, I would like to invite Dr. S.W. Anwane sir to start our first technical session. Dr. S.W. Anwane sir.
Thank you very much for your introduction. I recognize the presence of dignitaries, Dr. Nirulkar sir, Dr. Sote, my friend Dr. G.R. Avtar, and all participants. I'm trying to share my screen now. Is my screen visible? Am I audible?
Yes. Yes, sir.
Okay. Is my screen visible, Avtar sir?
Yes, sir. Yes.
Okay. I am going to talk on conflict of principles. And here, I am going to deal with a couple of aspects which are related to equivalence principle and information conservation. I'm going to talk about conflict of these 2 principles, which are well-established principles, and that is in pretext of black holes. Before starting my presentation and the interaction as a teacher, I would like to read a paragraph so that I should not miss the flavor of what I'm going to talk. Quantum mechanics is confusing. I guess you all will agree to me. One of its peculiar feature is different descriptions for same thing, and sometimes it is incompatible with our classical minds. That is, electromagnetic radiation behaves as wave sometimes and sometimes as particle. Not both at the same time. Particles has position and particles possess velocity, but not both at the same time. This is confusing. Electron has position and it possesses velocity, but not position and velocity simultaneously. All this has right name, that is called complementarity. They are complementary descriptions of things. At first sight, they look completely incompatible. The question is how nature avoids such contradictions. Nature does not allow us to measure these non-compatible quantities simultaneously. This we have learned in undergraduate physics. We cannot measure number of photons and their phase simultaneously. You can recall Heisenberg's uncertainty principle at this moment. We can measure one or the other. Thus, electrons cannot have position and velocity simultaneously, but electrons can have position or velocity. Black holes are very strange objects. Black holes in quantum mechanical world are even worse than that. They appear to contradict deeply held principles. So today I am going to speak on equivalence principle and information conservation. Now, let us go through our presentation. The equivalence principle is regarding the gravitational field and acceleration. A person on Earth can experience acceleration due to gravity 9.8 meters per second square. If the same person is in the outer space where there is no gravitational field, and if he is in the Einstein's elevator and this elevator is accelerated in a particular direction with the acceleration 9.8 meters per second square, it is equivalent to the gravitational field which is prevailing on Earth. That is what is the equivalence principle is. Now, the motion under uniform acceleration we have studied quite in early classes, I guess somewhere in the high school, and there we have established this relation. The position x at any point of time t is equal to position at the beginning plus 1 by 2 gt square, where the g is acting as acceleration due to gravity, and velocity you can charge g times t. Now you can let acceleration cause velocity comparable to velocity of light. So this velocity to reach to c, acceleration due to gravity, which is 9.8 meters per second square, it should enact for a couple of years. So 2 years, if you write in seconds, you will have velocity comparable to velocity of light. This is practically not feasible experimental situation, but our equations tell us that we can attain that velocity after a long time of action. Now, these equations are coming from classical mechanics, or you can say Newtonian physics. And here, x, if you chart this initial position at origin of the coordinate system, you can eliminate this, and x is directly proportional to t square. So this equation resembles the equation of parabola. So here we can sublime the values of interest, and we can write expression which looks like equation of parabola. And if you really try to plot the graph, you will be able to see the position which is prevailing on x-axis here, and time which is prevailing on y-axis. So if a physicist is drawing a space-time chart, it is quite probable that he will plot time on y-axis. Otherwise, the situation will be something like on the left-hand side of the graph. Now, these equations are quite all right as long as the velocities involved are very, very small as compared to the velocity of light. There is no issue if you are talking about speeds very small as compared to the velocity of light. But if you reach in the zone where the speeds are comparable to velocity of light, then you have to part away from the Newtonian mechanics, and special relativity we shall bring into picture. And in special relativity, we have interval x square minus c square t square is equal to, in fact, 0. This quantity is 0 in special relativity. And for another observer, another inertial observer, it is x dash square minus c square t dash square. This is also, I guess, everyone has learned during the graduate program. So special relativity deals with s equal to 0, and when s is not 0, that leads to the accelerated motion, and that leads to a space that we call Rindler space. So this is the story when the velocities are high, in the sense that velocity is comparable to velocity of light. Now, I shall be discussing the whole story by considering c equal to 1, so that this equation will have a simpler form, and I shall prefer to write x square minus t square equal to s square. So this is equation of a hyperbola. So we are rolling from parabola to hyperbola the moment we consider special relativity and general relativity. Now, when this quantity is 0, when we are talking about x square minus t square equal to 0, so this has two solutions. Rather, if we simplify this, it will be x square equal to t square, and that will lead to x equal to plus minus t. Now, when we are having a plot in xy plane, where x we reserve for space, so x is along x and time is along y-axis, then we are charting some graph where c is 1. So light will travel on right hand side this way and left hand side this way. So this will form a light cone. I guess everyone is acquainted with this basic diagram. Am I audible? Some. Avchar sir, am I audible?
Yes, sir.
Okay.
Yes, yes.
Okay.
Yes, sir.
Thank you. So in Rindler space, if you try to plot x square minus y square equal to 0, as I said, it will be this line which is passing through origin, and the opposite line will be like this. Now x square minus y square equal to 1 will have a parabola that will intersect with x-axis at 1, and so on. X square minus y square equal to 4 will intersect x-axis at 4. So this is the actual plot which I have carried out using this command in Maple. Now this is the, I shall try to close this. Now this is the Rindler space in which we have, if we have x square greater than t square, this is the space-like region, and when t square is greater than x square, this is time-like region, and the light is traveling, the boundary between two is called as light-like. Now, if something is not moving in this space-time diagram, then I shall state that the particle is present at this location of space. Let us call this as x equal to 1, and the object is not moving, it remains stationary, but the time is flowing along this vertical axis, so it will have a trace of trajectory which is indicated by this blue arrow, and that arrow indicates a world line which you call a world line in Minkowski space. So this is the object which is stationary, but in space-time diagram it is moving as animated on your screen. Now, if the object is moving, which is if the object is stationary, that remains at the origin of the coordinate system, then in space-time diagram it will travel along time axis. It will not have any change in the coordinate of its x-axis. Now the object which is moving in the space-time diagram will travel like this, that makes an angle with x-axis. So the light will travel along light-like direction. So if you call photon traveling, it will have to travel along a line that makes an angle 45 degree with x-axis. This is making 45 degree with x-axis because we have selected c is equal to 1 and the scale is normalized. Now, any actual motion will have a trajectory. If it is uniform motion, it will be charted by a line that makes an angle between 45 degree and 90 degree in this plane. Now, if you are talking about something moving faster than light, then that imaginary tracking will be along this line. And believe me that this is not permitted because nothing can travel in the space with speed greater than the speed of light. That is one of the assumptions of spatial theory of relativity, and this is a proven fact also by now. So this world line is not possible. However, all these world lines you can go on sketching that are possible. So the line that makes angle near to 90 degree is traveling with slower speed, and the line which is having inclination just above 45 degree is the speed close to the speed of light. So this structure I want you to understand. So a not moving object is indicated by this world line, and a moving object with more than half speed of the light is indicated by this line. However, this one is not permitted. Now, I really don't want to mention that this is a space coordinate and this is a time coordinate, but for reference, I have drawn it. Here we have light cone, which is indicated by two wave lines. One is indicated traveling along right hand side of your coordinate system, and another is traveling on left hand side of the coordinate system. They are making exactly 45 degree angle. One is making 45 degree angle with positive x-axis, another with negative x-axis. Now, here we have an observer who is accelerated in the frame, and as he is accelerated in the frame, he is tracking a parabola. Sorry, he is traveling around a hyperbola. And let us suppose that the observer is at this position, and this surface, which is a thick blue arrow, this is the surface that is representing either x-axis, or you can say that it is representing t equal to 0 surface or t equal to 0 line. The observer, when he is at next position, so that is indicated by a line that makes an angle, some angle with x-axis, and that is represented by a surface T equal to 1. Similarly, a surface T equal to 2, and the line which overlaps with the light like, that is T equal to infinity. Probably at the end, I have written this T equal to plus infinity. So this is the structure of time in space and time diagram. Now, the observer who is not moving, but he is flowing along time axis, whereas his time coordinate, whereas his space coordinate remains fixed. So here you can see that the object is traveling along a straight line and he is not having any change in the x coordinate. However, the time is flowing. Now, let us consider that the observer who is traveling along this hyperbola is Alice, and the another observer is Bob. So Bob is not moving, so he is traveling towards the light-like line, and that light-like line is the event horizon, and he is crossing the event horizon. Whereas Alice, who is accelerated along x direction, so Alice is traveling along the hyperbolic path with increasing velocity, and this hyperbola goes asymptotic to this time, this light-like line. Now, the velocity of Alice is ever increasing and it attains the velocity of light. So actually, no massive particle can attain velocity of light. So this hyperbola goes asymptotic to this t equal to infinity line, which is in fact x equal to t line in the xt diagram. So here the 45-degree angle is indicative of the slope, which is unity. Now, when Alice looks back, he can look back in this direction and can see the object here and can observe Bob present here. She can also look in the opposite direction and can see the object here. Now, this is the only visible region for the Alice. Now, here again, Alice is traveling along this direction, and here I'm changing the notation. So this is the t equal to omega equal to minus infinity, and another line is omega equal to plus infinity, which are the light cone lines, and omega is evolving in time, and that is reaching up to omega equal to plus infinity, which begins from omega equal to minus. Yes. Now, rho equal to 2. See, I'm going to raise this Rindler coordinates for you in the coming slide. So here s square equal to 2, you can imagine s square is equal to 2 square, and that quantity I am charting as rho equal to 2, and the object which is not moving, I mean the trajectory of the Bob, world line of Bob is indicated by this line, and Alice is traveling along this direction. So when Alice looks back, she can observe Bob here. At next point of time, she again looks back and can observe Bob at this point. So this is the line parallel to light-like line, and she can observe in this direction and see Bob. Now this phenomenon goes on increasing. Alice's speed is going on increasing, and when she goes close to this light-like line, her speed is close to the speed of light. So here you can see that the length of the bar, I mean the distance, that is increasing. As Alice has reached to this point and she looks back, she has to look at Bob here, and the distance between the two is indicated here by this arrow. So you can make the x coordinate of the distance, and you can realize that the distance is increasing. So the distance is increasing, that causes the effect that the time for light required to travel from Bob to Alice will take more time in this case. And as it takes more time, she feels that Bob is moving very slowly towards horizon. And how slow Bob is moving, that the Mr. Bob is taking eternal time to reach up to this point, because light is taking longer and longer time to reach up to Alice, and Alice feels that Bob is becoming slow and ever slow, and finally Bob is at the edge of the horizon but not moving forward. So for Bob, this is Alice's point of view. Now what Bob says, that his clock is ticking and he is advancing. In fact, Bob is not moving. Bob is sitting stationary, and time is flowing along this axis. So Bob is moving with time. At every click, every tick of the clock, he is advancing. Alice is skidding on the accelerated path, and see Bob is moving slow, and it takes eternal time to cross the horizon. Whereas Bob says that it is not so. I am moving across the horizon. There was no problem for Bob, and Bob has moved forward. So this is Bob's point of view. Now I'm going to the Rindler coordinates. So here I propose the coordinate transformation as x is equal to rho cos omega and y is equal to rho sinh omega. Why I'm talking about hyperbolic functions? Because I have hyperbolic geometry that we have seen, and the circular geometry coordinate transformation won't help me. And what is preserved is x square minus t square. Therefore, I'm proposing, Rindler has proposed the coordinate transformation using hyperbolic functions. So, rho square will be x square minus t square, and omega will be tan inverse of t upon x. So, these are the new coordinates that we have. And the hyperbolic tan function will have this kind of graph. It is for your ready reference, that omega can go from minus infinity to plus infinity, whereas tan of omega will roll from -1 to +1. Now dx, little change in the x coordinate we want, and here I am exploring the formula from calculus. First function into derivative of second function plus derivative of first into second function. So here first derivative of rho is d rho, and the second function remains as it is. Then plus first function into derivative of cos omega is sinh omega into d omega. Similarly, dt can be obtained from this. Derivative of first is d rho into second function plus first function into derivative of sinh omega is cos omega into d omega. Now what all I am interested in doing is I am interested in finding dt square minus dx square. And if you square these two quantities, if you like to square this, you have to use a plus b whole square. And similarly, you have to find dt square, and then you have to simplify this. You will come across d rho square minus rho square d omega square. Now, cos square minus sinh square is 1, whereas sinh square minus cos square will be minus 1. Therefore, this minus sign is appearing. You can try out in your free time. So here, what is omega and what is O? Omega is the time that accelerated coordinate system would use, and thus it is different than the ordinary time. Rho represents how far the hyperbola is located from the vertex of the light pole. This is tan inverse function for your ready reference. And here, omega is increasing in this direction. Omega is positive here, and omega is infinity at the light pole. And this is the Rindler space. Now, in this Rindler space, we have rho equal to 1, rho equal to 2, rho equal to 3. So these are the acceleration ways, and this is faster acceleration than this one. And now again we are back to the experiment of Alice and Bob. Now Alice is speeding on the accelerated path rho equal to 2, and she is traveling in this direction, and Bob is not moving, and she observes that the light coming from Bob, and she observes that light is taking longer and longer time when she is speeding on this accelerated path, and she observes that Bob is not crossing the horizon. So Bob, the situation is that she will see that Bob is stuck at the horizon. But what is Bob's point of view? Bob will say, what nonsense, I said through the horizon without trouble. So these are the two different perspectives. And now we are going to take this story, which is because of acceleration of Alice and Bob, to the concept of black hole, where instead of Alice acceleration to the speed of light, we are going to consider black hole. Now, if you have a bunch of Bobs, if you have number of Bobs, 1, 2, 3, 4, and 5, so what Alice will observe, Alice will see that all Bobs are clustered here at the horizon, whereas from the Bob's perspective, they will sail through the horizon without any trouble. So this is the story when Alice is accelerated, as I said, and Bob is not moving. The question is that whose point of view is correct? Alice is observing something, and Bob's experience is different. Now let us take this into the zone of black hole, and here we are using the equivalence principle. Now instead Alice is accelerated, we should consider the gravity because of the black hole. Now here we are asking Bob to jump into the black hole. So Bob is traveling in this direction, and this is the event horizon, which we call Schwarzschild radius. I am going to quickly tell you what is Schwarzschild radius in coming slide. And this is the singularity point where the things are very nasty. Now, Bob says that he is crossing the event horizon, that is Schwarzschild radius, and he is entering into the black hole without any problem. What Alice observes, Alice is observing that Bob is traveling towards the event horizon, and he takes longer and longer time to cross the event horizon, and she feels that when Bob is very close to the event horizon, Bob is squeezed to a pancake kind of thing. He is plastered on the event horizon, and she observes that he has trouble in crossing the event horizon. So Alice's point of view is that she sees that the Bob is piled up at the horizon. Bob takes infinite time to cross the horizon, whereas from Bob's perspective, he will cross the event horizon and he will enter into the black hole. The equations of general relativity tells that the person Bob will be squeezed and he will enter into the black hole and he will reach to singularity. Now, we are stuck at the 2 points of views. Does it represent two different descriptions? Is it an artifact of the funny coordinates? Is there need to make these two descriptions compatible? So these are the questions, and the answer to the question is yes, the description is compatible with simultaneity. As in the beginning, I was reading from a paragraph and I was talking about compatibility and I was talking about complementarity, and when we try to observe things simultaneously, we run into trouble. Probably that is the kind of thing happening here. Now, because of the gravity due to black hole, we are observing, I mean, Alice is observing a pile up at the event horizon, which is indicated by the Schwarzschild radius. And here, the information is piled up. So this is called as hidden information, and it is difficult to see the objects which are at the Schwarzschild radius. Why it is difficult to see? Because of the redshift. And the picture from mathematical description we have to raise, and it's hidden information, and black hole has entropy. This was discovered by Bekenstein sometime in 1972, something like that. Bekenstein's finding of entropy of a black hole and Stephen Hawking's finding of evaporation of black hole, they are supposed to be the landmark discoveries of 20th century physics. Entropy and hidden information, they are one and the same thing. We shall get into the zone of quantum mechanics now. Black hole, see, gravitating objects are major objects, and quantum mechanics we apply to smaller things which are in the realm of atom and molecules. But the highly gravitating objects like black holes, they are also tiny particles, and you need quantum mechanical approach to understand them. Black holes are hidden information and they give rise to entropy, where n is number of bits of information. So this law is nothing but the Boltzmann's law. S is equal to K log W. I prefer K equal to 1. I am not bothered about the proportionality constant at this point of time. A bit of information you can call elementary particle. A bit of information can be photon. So how much information a black hole can store? That's a question. And the answer is that it can store a lot of information. How much? Does it store infinite information? The answer is no. It cannot store infinite information. There is a limit to which it can store information. And the question is, what is that limit? So this was discovered, as I said, in 1972 by Bekenstein, who found entropy of the black hole. And in 1974, Stephen Hawking discovered evaporation of black hole. Now, I shall come to the basic definition of black hole, which Dr. Virulkar mentioned in terms of escape velocity. The formula for escape velocity is V escape equal to under root of twice gm upon r. Now, how this formula has arrived, we shall see. Basically, potential energy plus kinetic energy forms total energy of the system. Now, in terms of gravity, we shall talk about potential energy, and kinetic energy formula is very simple, that is 1 by 2 mv square. Potential energy, normally people talk about mgh, but the another form is minus gmm upon r, where m is mass of the object, which is whose potential we are talking about, and capital M is the gravitating object because of which the potential is prevailing, and r represents the distance between two. G is the gravitational constant from Newton's law. And as I said, potential energy plus total energy plus kinetic energy makes total energy, and kinetic energy is 1 by 2 mv square. Now, I want that the potential energy plus kinetic energy should be zero. The meaning of this is that you are supplying some kinetic energy to the particle so that potential energy plus kinetic energy becomes zero. Potential energy is negative, means you need to supply energy to escape that object from the gravitational clutch of the major gravitating object. So the minimum kinetic energy required to escape the particle from the gravitational clutch, we make total energy to be zero. So minus g m m upon r plus 1 by 2 mv square. So here v I am calling as escape velocity, because total energy is zero. It is the minimum amount of energy, minimum amount of velocity required to escape from that. It can be higher also, so that the total energy will be more, but we are talking about the mere escape. So if you simplify this equation, this will be, if you take it on right hand side, it will be plus, you can eliminate m, and then you can write this formula, the escape. Now, if the object has escape velocity, I'm talking about a situation when escape velocity is equal to velocity of light, or it should be greater than or equal to velocity of light. But any material particle, is there any problem? There was some message blinking on my screen. Am I visible and audible, Avchar sir?
Yes, sir.
Okay. I was
Yes, you are audible.
Okay, sir. I was perturbed because of some message that was on my screen. So, for minimum velocity required to escape, I should have V escape equal to C. Any material object will not be able to acquire the speed of light. So I want to replace escape velocity by velocity of light. So squaring this equation and assembling radius on left hand side and charting suffix s to that, that is the Schwarzschild radius. So you can find the Schwarzschild radius for Earth if you do that calculation. I remember that it appears to the peanut size 8 mm. If you crush Earth to the size of a peanut, then the radius, which is outer radius of that peanut, Earth is squashed to the peanut size. So at that point, the escape velocity will be velocity of light, and nothing will be able to escape from that black hole. So that is a hypothetical calculation which is prevailing in every book on this topic. So this is Schwarzschild radius. I guess I have explained you how the black hole is behaving, and here RS is this radius. This is RS. Now, if any object comes inside this, it needs escape velocity greater than the speed of light, and that is not feasible So it is trapped into the gravitational clutch for the eternity. Now we choose a photon of the size of Schwarzschild radius. Why we are doing so? Now let us suppose that this is a black hole. It means that this is the Schwarzschild radius of the black hole. And if I throw a photon at this particle, at this position, then it will have more information than a single bit, because where it is located, that's the question. So I'm choosing a photon whose wavelength is equal to the radius of Schwarzschild radius, so that that photon is of a single bit information. It will not have more information. And now my objective is that to add a single bit of information to black hole and see the changes. Now I shall prefer a photon. So here, this is the photon whose wavelength is this much, and this is equal to approximately equal to the Schwarzschild radius of the black hole. I am not choosing longer wavelength because it will bounce off. People have done these calculations that this photon may not be absorbed. If I choose a high energy photon, then this photon will hit at some point which will be localized, and my information will not be single bit information. It will be at which point it has hit the black hole, or at which point it has been absorbed by the black hole. And that will increase the coordinates, that will increase the information, and that information will be more than 1 bit. My objective is to throw a single bit information, and this is going to help me in the calculations, and these calculations were first done by Bekenstein. Now energy of photon is E equal to h nu. As I am adding energy, the increase in the energy delta E, that is h nu, that is energy of the photon. So nu is equal to c upon lambda. So that is equal to now I am replacing lambda by Schwarzschild radius. This makes a calculation simple. Later on you will see. Moreover, I am picking up Einstein's equation that comes from special relativity. E is equal to mc squared. If I perform a differential operation on both sides, and there I have to treat this c as constant, which is a universal constant, which is one of the hypotheses of special relativity. So treating that as constant, I can write change in the mass of the black hole I am going to talk about is equal to change in the energy of the black hole divided by d squared. Now, change in mass is equal to change in energy upon c squared, and change in energy we have estimated to be hc upon rs. So here we are substituting hc upon rs. So 1c is cancelled, and we are left with h upon rs into c, where rs is the Schwarzschild radius. But Schwarzschild radius, we know it is twice gm upon c square. Now we are interested in finding change in radius. So to find change in radius del rs, I'm using calculus formula that is equal to change in delta L, because 2 is a constant, g is a constant, and c is also a constant. So here I have change in mass formula, which I can substitute and I can combine to form change in radius is equal to twice g upon c square times change in mass, and change in mass is this much. So change in radius is equal to twice g upon c square into h upon rs into c. So in the denominator we have c cube. So by adding a single bit of information, which is a photon, the spatial radius of a black hole increases by this much of amount. So in the next slide, I'm going to carry forward this equation for discussion. So Rs is equal to twice GH upon Rs into CQ. This is out of catching of one information. Now I shall take this Rs on left hand side so that Rs into delta Rs will be of my interest. So you may feel that nothing has happened, but some advantage is there that Rs is delta Rs. This is radius into change in the radius of the black hole. So this is kind of area. Now area of a sphere is equal to 4 pi r square. Instead of r, I shall prefer to write rs so that we are talking about the spatial radius. Now, if you like to find dA,
Professor Anwane,
yes,
you please raise your voice
okay.
loudly, and I request all the participants and panelists, member of panelists, to mute because some disturbance is there.
Yes, I am also experiencing some disturbance. I also request all to mute their respective mics so that interference will be minimized. So change in the area, dA will be equal to derivative of r square will be twice r. So here it will be 8 pi times rs into drs. So my interest is that rs into drs, this is something like area when it is multiplied by 8 pi. So I am multiplying by 8 pi on both sides so that my equation is not disturbed really. And change in the area of the black hole is equal to 16 pi times gh upon cq. Now this quantity gh upon cq is having dimensions of area, and this is called as Planck area. If you like to find Planck length, you can find square root of this and it will be 10 to the power minus 35 meters. So this is the dimension of Planck length. So no two particles can be close than this distance. And dA, that is change in area, is 1 times. Why 1? I'm catching one bit of photon. So 1, that is not making any change, but I want to generalize this equation for n bits of information, and that gives rise to entropy. So 1 times 16 pi gh upon cq. So here we can replace 1 by s, and dA is the total area, whereas 16 pi gh upon cq is a small unit of area, which is increased by 1 bit of information. So we can rearrange this equation for s, and s is equal to a upon 16 pi gh upon cq, which is Planck area. So entropy is equal to area upon Planck area. And if we look at this equation, which is rearranged here and highlighted, this is a very, very important equation, a landmark equation, where we are talking about entropy. Entropy is represented by letter S. I think it is for the name Sadi Karnova, who first discovered entropy. A represents area, then area of the spatial radius, black hole we are talking about the surface area of that. C is the velocity of light that comes from Einstein's theory. Then G is the gravitational constant which is coming from Newtonian theory, and H is a Planck's constant that is coming from quantum mechanics. So here we have wired up an equation which is a combination of thermodynamics information, quantum mechanical information, relativistic information, and Newtonian information. So this equation has wired up almost all regions which are major parts of physics. So this is the celebrated equation which was first presented by Bekenstein. Now, the knowledge of thermodynamics tells us that the objects that possess energy and entropy that possess temperature. So I'm taking you into the zone of physics, and we have dE is equal to TdS. We must have learned it somewhere during your graduation. So the object that has energy and entropy that has temperature, therefore black holes also must have temperature. So we have dE, which is h nu upon c, and here we have entropy equal to 1. So temperature, increasing temperature by adding 1 bit of information will be hc upon lambda, and that we have added a photon of wavelength lambda, and that was of the order, that wavelength was of the order of Schwarzschild radius, which is twice gm upon c square. So here really we can calculate the temperature, and this is quite a funny result, that temperature is inversely proportional to the mass of the black hole. So here we have a bad news for Bob, that black holes have temperature, and that can be expressed by a formula that is appearing on your screen. So a bad news for Bob, that it's hot there. So in addition to what was happening from the perspective of Bob and Alice, there is one more problem, that there is a temperature, and black hole is warm. It is like a black body. This is WAR, warm, like a black body. So hot objects radiate, they radiate heat. So the black hole will also radiate its energy. This is allowed, and will eventually evaporate. This was discovered by Stephen Hawking. And how much time it will take to evaporate a black hole? It will take eternal time. Hawkins has given formulas for that. So in addition to what we were talking about, the situation, Bob is jumping into the black hole, we have temperature there. So black hole is radiating off, radiating photons, and the temperature is given by this formula hc upon twice gm. What Alice is observing, that Bob is traveling towards the black hole, and he is taking eternal long time to reach to the event horizon, and he is not advancing, that she is observing. Whereas the mathematical description of Bob's journey says that he will sail through the Schwarzschild radius and nothing will happen. And nothing will happen means Bob will be squeezed definitely, but Bob will travel into the black hole, crossing the event horizon. But Alice is observing while up, Bob will encounter photon of shorter wavelength. Shorter wavelength means higher heat at the horizon. Now, the temperature at a little distance d from the horizon will be hc upon d. Here I have replaced hc upon lambda. I have replaced lambda by d, which is the distance between the object which is at the outset to enter into the spatial radius. Now, as one goes closer and closer, it's hot and hotter. That is the information conservation law tells. But the equivalence principle says that Bob will travel across and nothing happens. Nothing in the sense that he will travel into, but definitely he will be squeezed. This is the real conflict. Now, Alice's point of view and Bob's point of view, every now and then we are comparing. So I shall quickly go through that. So information conservation talks about pile up and nothing is lost. It is hot near horizon. That is the perspective of Alice, and Bob, by equivalence principle, gets into the black hole and he hits the singularity. And at singularity, the things are nasty. He will be squeezed, that is for sure. But the two perspectives are struggling, which is right and which is wrong. Now, Bob hits singularity and not temperature, that theory of relativity says. And he cannot escape because he cannot travel with speed greater than the speed of light. Gravity is so strong there that he will be torn apart by the tidal forces. What is singularity? So in this Rindler space, this is the singularity. And once Bob enters into singularity, and he will not be escaped. He will not be escaped. So he is traveling this way, and some or other time he will hit the singularity, and whenever he will try with the speed of light, he will have this kind of trajectory, but he cannot escape through the black hole. So he will never come back to see Alice. So that is the place of singularity in space-time diagram. So he needs speed greater than the speed of light, which is not permitted. I'm just about to close my discussion. The real conflict is that general relativity says Bob hits singularity and not temperature. He needs speed greater than the speed of light to escape from that, which is impossible. Gravity is so strong there that it is for sure that he is torn apart by the tidal forces. It's deadly for the Bob. Bob will not survive, either by temperature or by singularity. That is the question which we are trying to understand. Which description is correct? Let's take a poll after observing this much and learning general theory of relativity. I would like to ask you a question, that whose perspective is correct? Bob gets trouble at horizon or at singularity? That is the question. So I would like you to keep answer in your mind what you agree with. But I think both descriptions should be made consistent. Now, let us try and fix the problem. We have third observer, Charlie, which is throwing light on Bob so that Alice can see him. And the distance at which Bob is there from the horizon, from the perspective of Alice, and that distance is really important, where we are replacing lambda by that d, and you need to throw light to observe the phenomenon. Now let us suppose that we have an atom present here, and we want to see whether, because of the temperature present there, whether the atom is ionized or not. And in attempt to see that whether the atom is ionized or not, Charlie is throwing light on the atom so that Alice can see. So you need radiation of longer wavelength because it is redshifted due to gravity, and in that attempt of increasing frequency of the radiation or decreasing the length of the radiation, will ionize that. Same will happen to Bob. In attempt of observing Bob, in this scenario, Alice is trying to see Bob and asking Charlie to throw light of higher and higher frequency or lower and lower wavelength, and in that attempt she will burn Bob. She will roast Bob. So if not hit by the singularity because of the radiation by Charlie, he will be roasted. Now we need to fix the conflict, and in order to fix the conflict, we try to see the experiment. We attempt to see Bob, and in the attempt of observation, we are spoiling our experiment. Whether the atom is ionized or not, we try to see, and in that attempt, we are spoiling the experiment. Now, both descriptions should be made consistent. They are not consistent, but they are complementary. Like in quantum mechanics, we describe position or velocity. We cannot tackle both at the same time. So in the same way, you cannot look from the point of view of Alice and Bob simultaneously. If we try both, we run into trouble. So two descriptions are, this is the present knowledge that two descriptions are not compatible, but they are complementary. Like we say that radiation has wavelength, or it is photon, it is particle nature or wave nature. It cannot be both. The same thing of complementarity is justified here to explain the conflict, and that is called as complementarity. So I am done with my presentation, sir.